All right, let's get right into it. Welcome to today's Explainer, where we're going to diagnose and fix one of the more intimidating errors you might encounter on your Teledyne API Model T300 carbon monoxide analyzer, the dreaded GFC Speed Warning. If you rely on this instrument for highly accurate environmental data, we all know seeing that error pop up can be a major headache. But don't worry, today we're going to break this down into a highly logical, step-by-step process to get you back up and running. Here's our game plan for today. We're going to cover the GFC speed alarm itself, understand the GFC wheel mechanics, perform a visual check of the status LEDs, diagnose the motor, test the optical pickup, and finally, correct the alarm. Section 1. The GFC speed alarm. First up, let's look at the exact symptom you're facing on the front panel. So why is your T300 throwing this warning? When this specific alarm hits, your analyzer completely halts its concentration readings. It doesn't just give you messy data, it flat out stops. And there's a good reason for that. The T300 relies on an internal spinning wheel to process its infrared light pulses. When the instrument detects that it's lost that critical synchronization, meaning the wheel is spinning at the wrong speed or it's completely stopped, the measurement math literally falls apart. The system throws the GFC speed warning to protect the integrity of your data. Moving to Section 2, understanding the GFC wheel. Before we go grabbing tools, we really need to know what this wheel actually does. Think of the gas filter correlation, or GFC wheel, as the absolute heartbeat of your 300. There's an element in there heated to about 1100 degrees Celsius, generating a broad band of infrared radiation. This physical, motor-driven wheel sits right in the path of that light. As it spins, it mechanically chops the IR beam, creating a measurable, alternating pulse for the photodetector. Now here's the really clever part. What's sealed inside that wheel? You've got two chambers. As it spins, the IR beam first passes through a measure cell filled with pure nitrogen, which doesn't absorb the IR light at all. Then it hits a reference cell packed with high CO, which strips out most of the IR energy at the 4.7 micrometer wavelength. This brilliant setup creates a high-low pulse ratio, letting the machine's processor calculate the exact CO concentration in your sample. To keep those pulses perfectly timed, that wheel has to spin incredibly fast and with absolute precision. We're talking exactly 1800 RPMs on 60 Hz power or 1500 RPMs on 50 Hz. The T300 uses a phase lock loop circuit to keep everything tightly synced. If that speed falters even a tiny bit, the sync drops and boom, you've got yourself a GFC speed alarm. All right, Section 3. Visual check for the status LEDs. So what do we do when that precise spin fails? We start with a very simple visual check. The analyzer is always running self-diagnostics, so let's hop into that. Safely open up the front panel of your running unit. Locate the sync/demodulator board and look right at it for two specific status LEDs, D1 and D2. Now, watch how they behave. If D1 and D2 are happily flashing away, you're getting sync signals and the wheel is actively spinning. But if those LEDs are completely dark, well, that immediately tells us we have a hard failure. Either the motor has physically stopped turning the wheel, or the optical sensor tracking it is totally blind. Section 4, diagnosing the GFC motor. Assuming those LEDs are off, our next logical step is checking the motor drive itself. Time to grab your multimeter. You'll want to measure the AC voltage between pins 1 and 3 on the connector feeding the motor. If your instrument is configured for standard 120 or 220 to 240 volt power, you're looking for about 88 volts AC. Running a 100 volt configuration, you should see roughly 100 volts AC. And hey, while you're checking voltage, do not forget the frequency select jumper, JP4, on the relay board. It needs to be installed for 50 Hz operation and missing or vertical for 60 Hz. So, if your voltage at pins 1 and 3 is good and your jumper is completely correct, but that wheel is still dead, you found your culprit. The GFC motor has officially failed and needs to be replaced. Section 5. Testing the optical pickup. But what if the motor is getting power and it's physically spinning, but you still have the alarm? If the wheel is spinning, the machine just isn't seeing it spin. Let's look at the optical pickup sensor, which uses an LED and a detector shining through a mask on the wheel to track rotation. Hook up an oscilloscope to test points TP1 and TP2 on the opto pickup board. We are hunting for absolutely perfect square waves here. The shape of that wave tells you everything you need to know. Clean, sharp, square waves? Your sensor is perfectly healthy, and the issue is likely further down the motherboard. But if you see a distorted, noisy, or totally flat wave, that sensor is struggling. It's either blocked by dust, physically knocked out of alignment so the light can't pass through, or the electronics are just completely dead. Section 6, correcting the wheel alarm. We've traced the root cause down the funnel, so let's finalize the fix. The Teledyne manual doesn't mince words here. It says straight up, if those TP1 and TP2 waveforms are bad, the opto pickup is most likely shot and needs a full replacement. So, depending on what you found in the diagnostic steps, your path is clear. Slightly distorted wave? You might get lucky just carefully cleaning the optical sensor lens. Good voltage but no spin? Swap out the motor. Dead sensor waves? Replace the entire opto pickup assembly. And please remember to actually turn off the analyzer before removing these components so you don't accidentally fry the circuitry. By methodically working through this, understanding the pulse mechanics, checking those sync LEDs, verifying motor power, and scoping out the electrical test points, you take all the guesswork out of the repair. You can quickly clear that GFC speed alarm and confidently trust your environmental data again. But really, when you step back, isn't it kind of wild to think about how many massive environmental decisions globally rely on a tiny, spinning wheel perfectly chopping an invisible beam of light? Keep that in mind next time you look at your data. Thanks for tuning in, and I'll catch you in the next explainer.